All right, grade 11s. So I know that first video was incredibly exciting. So the next video, this one, really important, really part of the first lesson. But anyway, we're going to talk about Newton's laws of motion. And Newton's laws are like epic because like they really change the way we think about our place in the universe and the whole universe itself. Anyway, we'll talk more about it later. But look, the laws are really simple. They refer to any object anywhere and what governs the motion of these objects. Okay, so just basically rules that these objects seem to be following. And yeah, so let's go through the laws. I thought before we look at the laws, one of my favorite guys to follow on YouTube is the slow-mo guys. So in this video, it's really funny. One of the guys gets a soccer ball filled with water, so it'd be quite heavy, to the face, and they just recorded it in slow motion. And you know, because his face gets hit by this force, this impact force, a lot of the laws are like, kind of clear here. So watch. In fact, the first three laws, you'll be able to see all three in action here. I'm just going to play this. Okay, so here comes the soccer ball, and then it hits him in the face. Okay. Notice what happens to the ball. I know the face is the sort of the primary thing, but the ball just sort of sits perfectly still and the motion gets transferred into his face. Okay, so the ball's moving at first. All right, now watch his nose. His nose almost looks impossible. His nose will seem to bend like in an almost impossible way. It looks like it's broken. Okay, but it's actually lagging behind, and his mouth lags behind too, as his head starts to move very quickly to the right. Okay, so there you see it. I'm just going to pause it right there. Okay, and that is it's too bad we can't try that ourselves, of course. I don't know how he doesn't get concussed. But anyway, so in that little collision that took place, you can see Newton's laws, and I'm just going to tell you the laws. There's three kind of the most famous ones, but the fourth one is gravity, which is really his best work. Okay, we'll talk about gravity a little bit later, but let's just talk about the other laws. Okay, so law number one. His face was initially at rest, right? And objects at rest actually tend to stay at rest. And objects in motion, like the ball was initially in motion, they tend to stay in motion. Okay. Now maybe you don't get a sense of it from watching that collision take place, but think about, let's say, your phone sitting on the table. It tends to stay at rest, right? If it were to suddenly fly off the table for no reason, I think that would scare you. Okay, so yeah, objects tend to do what they're already doing. Okay, and that's law number one. So law number one, I'm just going to write it down here. There's a name for it. We call it inertia. Okay, and inertia is the tendency of an object. I'll just write it like this. An object at rest tends, okay, to stay at rest. Now, by the way, if you don't want to watch these videos, if you just want to go straight to the notes and just read them on your own or read the textbook, that's entirely up to you. But if you want to listen to my explanation, I might add some details that will help. Okay. Now, there's a second part to this. An object in motion tends to stay in motion. But the key is it's a very specific type of motion. It's a uniform velocity. And since velocity is a vector, it means a constant speed, but also a constant direction. Okay? So you can't change direction. It has to keep the direction the same. So in other words, objects tend to move in a straight line, okay, at a constant speed. That's how they tend to move. Now, it doesn't mean that objects have to do that, okay? I mean, this is only the first law. There are other laws, and the other laws will explain what happens when objects don't do this, okay? But that's what objects naturally tend to do, okay? They tend to stay at rest. Like, for example, an object sitting at rest on the table, that makes sense to you probably. It's not just going to start moving all for nothing. However, picture rolling a marble or something across the floor. It doesn't just change direction for no reason. Like, it will change direction if something were to come into contact with it, like some kind of force were to knock it off its path. But otherwise, it'll move in a straight line. Okay, and that's what it'll tend to do. Like, it doesn't just suddenly or spontaneously change direction for no reason. Okay, so that is called inertia, the tendency to do that. And one more thing about inertia, the more mass you have, the greater the inertia you have. So mass is the key property. Okay, so more mass equals more inertia. I think you have an intuitive sense of that. Like, if a truck is driving down the street and you get out of the way, like, it has a lot of inertia. It's going to just go right through you. Okay. However, if a ping pong ball is heading your way at the same speed as the truck, that could hit you, and the ping pong ball just doesn't have enough inertia to get through you, right? So it just bounces off. All right, number two. Number two is what happened to this guy's face when the ball hit it. Okay, so when the ball hits his face, it exerts a force on his face, and here you can see it. Okay, it exerted a force on his face, and that pushed his face to the right. Okay, you can see the inertia in his nose, though, and in his mouth. They're trying to stay at rest. They tend to stay at rest, and so what they're doing is they're trailing behind the movement of his skull. Okay, so anyway, so you can see some inertia there. However, the ball pushed his head, and it pushed it pretty hard to the right. And when objects experience a force, like an unbalanced force, they will accelerate in the direction of the unbalanced force. And that's kind of logical too. And so that's Newton's second law. Okay, so let me get to that here. Okay, so really it's just an equation, but I'll write it down. When an object experiences an unbalanced, and that's the key word, like unbalanced force. And what I mean by that is, like, you sitting on a chair, like I'm sitting on a couch right now, me sitting on the couch, I'm not accelerating anywhere because gravity is pulling me down, let's say, that's one force acting on me, but the couch is pushing me up. So those two forces balance each other, and then I end up not accelerating anywhere. Okay, so if the force is unbalanced, you take the chair away and the person falls, right? So now we see that gravity would be an unbalanced force. You drop something out of your hand, it falls because of gravity. Your hand is balancing the force of gravity. Then when you drop something, it's unbalanced, and so it falls because of gravity, accelerates downwards. So when an object experiences an unbalanced force, it accelerates in the direction of that force. Okay, now it's really these words don't do it justice, so Newton wrote an equation. The amount of acceleration you get is proportional, not equal to, but proportional to how much force you get. Okay, so we call this the net or unbalanced force. We sometimes call the net force acting on an object. So what proportional means, this little weird Greek symbol, what it means is, let's say a force of a certain amount of force were to accelerate a ping pong ball at 3 meters per second squared. Okay, now if I double the force, it would accelerate the same ping pong ball at 6 meters per second squared. So that's what proportional means. You double one, you double the other. You triple one side, you're going to triple the other. But it doesn't mean they're equal. Like a force of 10 could give me an acceleration of 3 meters per second squared. There's something else that determines the acceleration too. So let's talk about that. Acceleration also depends, that's an A, on how much mass you have. So that guy's face in this video has a certain mass. Okay, now let's say that soccer ball, which is very heavy, were to hit something smaller than his face, a smaller mass, it would accelerate even more. Okay, so if it were to hit a small tennis ball or something, it would accelerate even more than his head would. His head's attached to his body, so it's actually quite a bit of mass there. So acceleration depends on two things, how much force you have, but it's inversely proportional to mass. The more mass you get, the less acceleration you get. Okay, now putting these two things together, Newton's equation looked like this. A equals the net force divided by the mass. Okay? Now, rearranging it to solve for force, you get F net equals ma. And this is usually how we write the equation. So I'm going to put a little box around this. That's Newton's second law. So usually if I ask you on a test, what's Newton's second law? You just say F equals ma. That's the law. And really, the words describe that law, but the equation describes it even better. Okay. Now let's talk about the units of force. So how do you measure force? What are the units? Well, the unit of mass, the standard unit is kilograms. Okay. The unit of acceleration, oh, I won't write equals. I'll just write a little arrow, is meters per second squared, right? So if you multiply those units together for force, you would get kilogram times meter per second squared. Now that was actually Newton's units, okay, in Newton's day. You just kilograms times meter per second squared, right? But we, in honor of him about 40 years ago, changed this to, I'll just say 1 kilogram times meter per second squared. We renamed it 1 Newton. And from now on, and this gets a little confusing, 1 capital N. Now that doesn't mean north, okay? Like force is a vector, but capital N means Newton. If it was 1 Newton north, I would have to put square brackets like this means north, right? Outside the bracket, it means newtons. It's not the same thing. This is a unit of measure, newtons, right? And if you want to get a sense of what a newton feels like if someone to push you with 1 Newton, just hold an apple in your hand. The weight of the apple is about a Newton of force. Okay, it's about the force of gravity on 100 grams of mass. Okay, is about 1 Newton. All right, so that was our Newton's first 2 laws. We'll talk about the third and fourth law later, but for now, that's it. So you have 2 laws, inertia, which we honestly is not going to come up very much in the questions. But law number 2, this one here, that's your first assignment, is going to be based on that equation. It's pretty straightforward, but you're going to need my help with some of the questions. So we'll go through the assignment. Just let me show you where the assignment is. I posted it in here. I don't expect you to answer all of these questions right now based on what I've said already. But if you just look at these questions here for a moment, let's see if we can do a couple of them together. Okay. Notice the answer is posted, like there's the answer to the first question. Okay, so that's for you to check your answer. I will always do that while we're doing this online thing. All right, so let's look at question number 1. How much force did the expanding gases in a gun barrel exert on a 6-gram bullet as it accelerates from rest to 500 meters per second in a 0.7 meter long barrel? All right, we're still talking about motion. So I know this is a very violent question, but anyway, maybe he's not. Maybe he's only target practice, so it's okay. But anyway, look. Yeah, basically you're going to answer that question by using F equals ma, right? So this is question number 1. Now, how would you find? They give you the mass, but the mass has to be in kilograms. So I'm going to write down 1 gram, but that is 0.001 kilograms. You have to divide that by 1,000. You have to use kilograms. Okay, very important. Standard units, meters, kilograms, seconds in physics. So kilograms is standard unit of mass, not grams. All right, now to find A, you have to go like this. It starts from rest, the bullet. So V1 is 0. V2 is 500 meters per second. The displacement inside the barrel is 0.7 meters. Okay, I'm just reading the question and writing down the information. A is the one we want because I need the acceleration to answer the question. And time is don't care. Now, if you've been paying attention at all this semester, you see what I'm doing here, right? We're going to use this equation, V1 squared sorry, v2 squared, equation number 5, v2 squared equals v1 squared plus 2a delta d. Solve it for a, okay? And then bring that number back up here and go F equals MA. I guess I should write it. 0.001 is the mass, and then you're going to multiply that by whatever you get for the acceleration. Just going to fill in the blank in there for the acceleration. So you have to do 2 steps. Number 1, use a motion equation to find acceleration. Then use F equals ma to find the force. And that's it. You should get the answer that they give you here. Okay? All right, so that's question number 1. Now I want to tell you, in order to answer question number 2, okay, we have to talk about gravity. But so I want to give you this so you can at least do the first few questions here. But don't forget, okay, don't forget to do, please, the textbook homework. So I want to show you that right now. This is the textbook homework. Okay, so these 2 lessons here, you should be able to do both of those. And if you're confused at all, read the textbook. It's additional support for you. It's additional information. I know I never ask you to read it when I'm teaching you in person, but it's kind of important here. Okay. All right. So, getting back to this. Okay. Let's talk about gravity for a second. Okay. So gravity near Earth. Okay. So you know, okay, if I were in class, I would ask you, what's the acceleration due to gravity? Right? What is it? What's the number? Well, you already know that the acceleration due to gravity, and we're going to use a different letter from now on, we're going to use g instead of a for it, is just 9.8 meters per second squared down. Now that's here on this planet, basically anywhere you go. Okay? Now that tells us something about the force of gravity on something. So the weight of an object is not its mass, which most people get confused with. It's the force of gravity on a mass. So my mass is 75 kilograms, but my weight is not 75 kilograms. Or a certain number of pounds, let's say 180 pounds or something. It's not 180 pounds either. My weight is measured in newtons. It's how much force is acting on my body because of gravity. And to get that number, I just use Newton's second law. So therefore, the force of gravity on an object is just mg. And this is your weight. Okay? Like it's really what weight is. Not what you think. It's not pounds. Not really technically speaking. You're using it, when you say it's a certain number of pounds, you're telling me your mass, not your weight. Okay? So anyway, that's your weight. Now it's really important when you're answering the questions, okay, in the little assignment, and I prefer if you just do the textbook homework for now, and then in the next lesson I will show you how to do these worksheets. I'm going to have to teach you how to draw a free body diagram in order for you to answer most of those questions. All right, so I'm about 18 minutes into this video. I think that's enough for now. So my next lesson, I will teach you a really, really, really important lesson on how to solve questions using what's called a free body diagram. Then I'm going to give you opportunities to ask me questions when you try these worksheets and see if you can answer them. All right, so that ends my second video, guys. I hope you're enjoying it. I know it's so exciting. Okay, so I'm signing off. I will see you next time.